Good morning. Let us now start with exercise 2.2 and see how to deal with the questions there. The first question is 3 sine inverse x is equal to sine inverse 3x minus 4x cube. Now let me remind you students, before doing each of these questions, you would have to revise all the identities which we did in class 11. Only then you will be able to these questions smoothly. Okay, so now the procedure for solving such questions is the same as we did for the proof of properties. That is, we assume the trigonometric function on the left hand side to be something and substitute it in the right hand side to do the needful. So let's start. Let sine inverse x is equal to theta. This gives us x equal to sine theta. With this, the right hand side becomes sine inverse 3x minus 4x cube is equal to sine inverse 3 sine theta minus 4 sine cube theta. If you recall, this is the result for sine 3 theta, and so we get sine inverse sine 3 theta, and this gives us 3 theta. Substituting back the value of theta, we get 3 sine inverse x, which is nothing but the left hand side, and thus we have proved this result. In the same manner, question number 2 can be done with assuming the left hand side function, which is cos inverse x, to be theta, and following the similar steps. Now let's take up question number 3. Now we have tan inverse 2 by 11 plus tan inverse 7 by 24 to be proved to be equal to tan inverse 1 by 2. Now for this we will be using the result for tan inverse x plus tan inverse y. So first let's see that what is the product of x and y here, that if x is 2 upon 11 and y is 7 upon 24. So 2 by 11 into 7 by 24. Clearly it is less than 1 and it falls in the category of the first result, that is tan inverse x plus tan inverse y is equal to tan inverse x plus y over 1 minus xy. Now it is very important to check this before applying this result, because as you are already aware, in case we had got xy to be more than 1, we would have had to use another result, that is tan inverse x plus tan inverse y is equal to pi plus this thing. Now let's start with the left hand side. Now here we can directly apply this result, and so we start with the left hand side. So left hand side gives us tan inverse, now this plus this, that is 2 upon 11 plus 7 over 24 over 1 minus 2 upon 11 into 7 over 24, which on solving gives us tan inverse. Now you write 2 into 24 plus 7 into 11 upon 11 into 24, 11 into 24 minus 2 into 7 upon 11 into 24. Clearly this gets cancelled, and this on solving gives us tan inverse half, which is equal to the right hand side. Same way we can do question number 4, and in that what we do is, if you just see, question number 4 says 2 tan inverse half plus tan inverse 1 by 7 is equal to tan inverse 31 by 17. Now if you observe in the left hand side, there is a term that is 2 tan inverse half. So first of all, what we do is we will solve this. Now we know that from the properties, if you see, 2 tan inverse x can be written in 3 different manners. One is in terms of sine inverse, one is in terms of cos inverse, and the third one is in terms of tan inverse. Clearly here, since we have to prove or add it to a tan inverse function, so first we will write this in terms of tan inverse. So we start with the left hand side, write this in terms of tan inverse. So this comes out to be tan inverse 2x, that is 2 into half, over, then we have 1 minus x square, that is 1 minus 1 by 2 whole square, and this remains as it is. Then you solve this and again apply the result for tan inverse x plus tan inverse y, which will lead you to the right hand side. So try these questions and then get back to me in case of any doubt. Now we start with the next kind of questions, which starts from question number 5 onwards. Now to deal with each of these questions, we have to first do a list of substitutions and you have to remember them. So let's first consider the list of substitutions to be made. And this list is extremely important as this will be used even in the chapter of derivatives. So when we are dealing with derivatives of inverse trigonometric functions, over there also it is extremely important. Okay, now there are certain set functions and the substitutions to be made, and the list is something like this, that whenever in a function you come across a term like under root of 1 minus x square, we always make the substitution x equal to sine theta or cos theta. Out of this, the preferred one is sine theta. So when you substitute this, what will you get? This becomes equal to 1 minus sine square theta, which is equal to under root of cos square theta equal to cos theta, which can be easily solved further. Similarly, now if you have one, though using cos theta also you can simplify it, but the preferred substitution is sine theta unless and until the question demands the choice of cos theta. Now similarly, if you have under root of 1 plus x square, we will put x is equal to tan theta, or you could also put cot theta, but the preferred one is the tan theta. And how does this get solved? 1 plus tan square theta, which is equal to sec square theta, which is sec theta. Similarly, we can do using cot theta also. Now in case you have a function like let's say you come across now we have done these two. Now the next one is, suppose we come across 1 minus x under root. Okay, so for this what we do is we put x equal to cos 2 theta or simply cos theta. So what we get is, when you substitute, you get 1 minus cos theta under cos 2 theta, which gives you 2 sine square theta under root, and which can be solved as root 2 sine theta. In a similar manner, if you have 1 plus x under root, you put x equal to again cos 2 theta, or cos theta will also work, but the preferred version is cos 2 theta, and we get 1 minus 1 plus cos 2 theta under root would be equal to 2 cos squared theta, which can be further solved, and you will get something like this. Same manner, if you have 1 minus x over 1 plus x under root, or 1 plus x over 1 minus x under root, then in that case what we do is same substitution, that is put x equal to cos 2 theta, and this gets solved to 1 minus, let's take this one, so 1 minus x over 1 plus x under root gets solved to 1 minus cos 2 theta over 1 plus cos 2 theta whole under root, which gives us 2 sin square theta over 2 cos square theta whole under root. This gets cancelled. This gives us square root of tan square theta, which gives us tan theta. Same way we can make the substitution in this, and we'll get a cot theta as a result, which can be further simplified. Now another substitution which can be used in case of absence of square root sign in such functions. We can carry on with this, or we can also put, this is the same case also in 1 plus x over 1 minus x. In both these cases we can put x equal to tan theta. Now how does this help us? 1 minus x over 1 plus x will be equal to 1 minus tan theta over 1 plus tan theta. In place of this 1 we can write as tan pi by 4 minus tan theta, and here we write this tan theta as 1 into tan theta. So 1 can be replaced with tan pi by 4 into tan theta. This gets solved to tan of pi by 4 minus theta. Similarly, we'll get 1 plus x over 1 minus x as tan of pi by 4 plus theta. Now another kind of substitution which we can use sometimes depending upon the need of the question is that if we have to deal with 1 minus x under root, or we have to deal with 1 plus x under root. Sometimes we also put x equal to sine 2 theta or simply sine theta. Preferred version is sine 2 theta. So what do we get? 1 minus x under root can be written as 1 minus sine 2 theta. Now we know that cos square theta plus sine square theta is equal to 1. So we replace this 1 by cos square theta plus sine square theta, and this gets carried down as it is, that, and you can write it as 2 sine theta cos theta. Now clearly this is nothing but cos theta minus sine theta whole square, and the under root and the whole square gets balanced, and we simply get back cos theta minus sine theta, which can be further dealt with. Same way 1 plus x whole under root can be written as 1 plus sine 2 theta whole under root, which can be written as cos square theta plus sine square theta plus 2 sine theta cos theta whole under root, which gets solved to cos theta plus sin theta whole square whole under root, which gets solved to cos theta plus sin theta. We'll do the question number 5 onwards in the next video. Thank you.